Alright, in this video we're going to look at more mirrors. In particular, we're going to look at convex and concave spherical mirrors. The first one we want to look at is categorized as concave. It's easy to remember that if you think of mirrors that have been caved in, so that the light will be coming in on this side. The other type that we'll look at the end of this section is called convex mirror. And those are mirrors that would bulge out like this, so that the light was coming in and hitting like this. Both types of mirrors are used fairly often, but for slightly different purposes. So let's look at the concave first. There's a concave mirror. If we draw a line that goes right through the center, that line through the center is called the principal axis. It's also sometimes called the optic axis. This is a curved surface like a circle or a sphere. There is a location that would be called the center of curvature. I'm going to put my center of curvature back here. And there's another point halfway through. So C is the center of curvature. That means the radius would go from that point all the way to the mirror. And point F is called the focal point. And then, of course, what he said, we have two other really important. R is the radius of curvature. And F is what we call the focal length. Okay. For a concave mirror, the radius of curvature and the focal length are both considered to be positive. The focal length is probably the most commonly referred to number in describing the way a mirror behaves. The relationship between these two is that the focal length is exactly half of the radius of curvature. All right. Convex mirrors can also be considered converging mirrors. What happens with a convex mirror is that any rays that are coming in that are parallel to the axis, as long as they're not too far from the axis, I'll draw some coming in perfectly parallel. By perfectly parallel, I mean I'm eyeballing it. So if I have parallel rays coming in, and a really good source for parallel rays is actually the sun. Because the sun is so far away from us, any rays that reach us are for practical purposes parallel. Incoming parallel rays are always reflected back through the focal point. And I could draw this with my yardstick a little neater. Now, I drew that like there's really a sharp focal point. And if this was a parabolic mirror, parabolic mirrors do focus exactly at the focal point of the parabola. For spherical mirrors, it's approximately focused there. We get what we call a little bit of spherical aberration, so it's not quite as sharp. But nonetheless, if I took this type of mirror and I took it outside where the sun was and I aimed it towards the sun, it would focus where it looked like the image of the sun was right at that point. One of the things we also know about light rays is their paths are reversible. So instead of starting with parallel rays, if I started with a light source right here, like a light bulb that went out in all directions, most of the reflected rays would actually go back parallel. So we have a couple of common uses for this type of mirror. One use is to focus parallel rays. You can focus the sun's rays and start a fire or something terrible. The other thing though, we use these in things like car headlights, because if we put the headlight bulb right here, that curved surface will cause it to go out more like a beam instead of just light out in all directions. These types of mirrors can form a couple different types of images. One of the primary uses that we do with these is they make excellent magnifying mirrors. If you have a shaving mirror, a makeup mirror, it's probably going to be this type. Let me show you how the rays work, how we get what we call image formation. Here's the mirror, and here's the axis. And I'm going to say that that's the center of curvature and that's the focal point. So here's F, here's C. If I put an object, and we usually use something like an arrow, let's put an object so that it is, for our first example, let's put one in front of the focal point. When we put one in front of the focal point, that's when we get magnification. And so when you stand in front of a makeup mirror, it may feel pretty flat because its focal point may be kind of far back there. But here's what's going to happen. Let's look at what, if we have an incoming ray that's parallel to the axis. Try to draw it pretty parallel right across the tip of that arrow. It will reflect like this. Now, if you're back here looking at your picture of yourself or whatever, your eye only sees the direction that ray is coming from. It can't really tell where it originated. It can't tell that it's coming from this way necessarily. It sees it as if it's coming from there. That's one ray. Let's look at a second ray. Let's consider a ray that came from through the focal point, like this. Well, any ray passing through the focal point, right across the tip there, there's an incoming ray, goes through the focal point, right across the tip, it's coming in like this. It will reflect parallel. You go, well, how does that image go? Well, if we back this up, this looks to your eye as if it may be coming from back here. So your eye sees a green ray coming out, it sees a blue ray coming out, and it appears as if this arrow, this object, is back there. Okay, so that's when we put the object in front of the focal point on this type of mirror. It acts like a magnifying glass. This image is virtual because it's back here where there's no actual light. Just like when we look in a regular bathroom mirror, we get a virtual image, and it's upright. All virtual images are upright. We can also see that it's magnified. I'm not going to put any numbers here, but I just want you to see how it behaves if we put something in front of a concave mirror, but in front of the focal point. Let's do that same kind of image drawing, only this time let's look at what happens maybe if we put it in a slightly different place. Let's put it, let's erase this. We'll erase these rays we drew. And this time, I'm going to let the object be back here. This time I'm going to put it past the focal point, between the focal point and the center of curvature. But the main thing is I want it out past the focal point. When it's out past the focal point, we get a different type of image formation. First again, we start with what happens to a ray that comes in parallel. So this ray that comes in parallel will always reflect right through the focal point. Let's hope I left enough room on the left side. And let's do another ray. This ray is coming from the object towards the focal point. Oh, I don't know if I left enough room. I may have to move my object or something. Oh, probably just barely. It will also reflect back parallel. You can see my green ray and my purple ray meet here. Before, it looked as if they met it back here. Now, I probably need to have my person back up a little bit. Leave my eyeball. But the image that's formed this time looks like this. When we put this object farther back, this type of mirror forms what we call a real inverted image. If we put a screen, like a movie screen or a sheet of paper back here, we would actually be able to see the light would actually form a picture right there. Your eye acts not like a convex mirror, but what we call a converging lens. And when we have images form on our eyes, this is a mirror, not a lens, it's a little different, but it forms a real inverted image. The pictures on your retina, if you could see them, are upside down. You see things right side up because your brain takes that upside down image and flips it over right side up. Okay. But those images are real. Anytime you have a real image, it is inverted. Okay, so you can, if you do what we call ray diagrams, and you draw everything perfectly to scale, you measure everything very precisely and pay attention to all your angles, you can do a good job of locating where images would be located with rays. But that's certainly not the easiest way. We usually use our equations. And we use our equations. There are basically just a couple. They're called lens-mirror equations. So the nice thing is, if we learn the formulas for mirrors, these are the same formulas you would use for lenses. And the first one is that 1 over the focal length equals 1 over the object distance plus 1 over the image distance. The only thing you need to know is that for concave mirrors and converging lenses, F is always a positive number. If you have the other case where you have a convex mirror or a diverging lens, the focal length is always a negative number. So we sometimes call these types of mirrors and lenses negative lenses or negative mirrors. We would consider these to be positive lenses or positive mirrors. But the equation is the same. The magnification is simply the ratio of the image height to the object height, which happens to be equal to the negative of the image distance over the object distance. Now, when we talk about a negative height, that just simply means the object is inverted. If the object's right side up, magnification will be positive. If the object's upside down, magnification will be negative. So we've got two formulas, pretty straightforward. So we probably are ready to work an example. First example is going to be chapter 32, example 4. It deals with a concave mirror. And that concave mirror has a radius of curvature of 30 centimeters. The object distance, is 20 centimeters. So we put the object at 20 centimeters in front of the mirror. And the object has a height of 1.50 centimeters. We'll just find everything we can possibly find. The first thing we always want to find is our focal length. Our focal length is r over 2. So in this case, it's 15 centimeters because 30 divided by 2 is 15. We can locate the image. 1 over f equals 1 over do plus 1 over di. Now, I probably would just type this into a calculator and solve for di. 1/15 minus 1/20, we'll get a decimal, then you'll take an inverse. It's certainly possible to do these types of problems by hand. The least common multiple that I see jumping out at me is 60 di. If I multiplied everything by 60 di, that would be 4 di equals 3 di plus 60, which means that di has to equal 60 centimeters. And that is, of course, the correct answer. Like I say, I don't usually do it by hand, but if the numbers are nice, it's not hard to do. If we wanted to know magnification, it's negative di over do. So negative 60 over 20 is negative 3. If I wanted to know what the height of the image is, it would just be the magnification times the height of the object. Negative 3, 1.5 centimeters. What the negative magnification is telling us is that it is inverted. It is upside down. Or really that's what the negative, image height. If it's upside down, then this is apparently a real image. Real images are always inverted. There is another problem, very, very similar. We'll work it real quick. We're going to keep the same mirror that has a focal length, of course, we've already found. Since the radius of curvature was 30, we know our focal length is 15. Only this time we're going to move the object to 10 centimeters. Okay, we'll keep the same. We'll keep the same height object. I think they changed it, but I'm not going to change it. But the difference is now we're in front of that focal point, closer to the mirror instead of behind it. So now when we do this, 1 over f, so 1 over 15, equals 1 over the object plus 1 over the image distance. This time, if I wanted a common multiple for 15 and 10, I could use 30. So the least common multiple is 30 di. So I'm going to get 2 di equals 3 di plus 30. That's going to give me negative di equals 30, or di is negative 30. That negative image distance tells me that this is going to be behind the mirror. When I do the magnification, it's negative of negative 30. That's negative do. Sorry, it's supposed to be negative di. It's the wrong word. Over do. That one comes out to just be positive 3. So this time, our object, our image, is going to be positive 4.5 centimeters. The fact that the magnification is positive tells us that it's upright. The fact that it's upright tells me that it is a virtual image. The real images are always upside down. All right. That should give you a pretty good understanding of concave mirrors. When you look at convex mirrors, they're similar and yet they're different. One, they have negative focal length. F is less than 0. They don't focus parallel rays. The concave mirror focuses those parallel rays. These cause the parallel rays to diverge or to spread farther apart. And these always form small, virtual, upright. Every virtual image is upright images. So here's what we have. If we were to draw our axis, this time our focal point and our center of curvature are actually behind the mirror. They're back here. Typically, this type of mirror is used either like rear view mirrors on a car or side view mirrors, or real frequently also used as security because they'll take in a wide angle view and compress it down. So you see these in the corner of all the 7-Elevens. So there's some object out here. What happens? Let's look at a couple of what we call principal rays. If we take a ray, get a different color here. And it's parallel to the axis. to reflect, but it's going to reflect as if it comes from the focal point. So it's going to go off like that. If we follow this ray back, it would appear to come from the focal point. So there's that ray if we follow it back. If we have another ray that also goes across the tip that's directed directly toward the focal point, when it hits the mirror, it reflects parallel. So it's coming in like this, but when it hits the mirror, it reflects like this. You can see that if you're the observer out here and your brain is tracking these rays back, it appears as if the object's right here. Now, this type of mirror does not magnify the image at all. This gives you a very small image. That's one of the reasons on the side view mirror on your car, it makes the comment that cars may be closer than they appear. Because since the cars appear so small, there's a tendency to think those cars are farther back than they are. Okay? The math is exactly the same. The only difference is anytime we're doing a problem that involves a convex mirror, we know that the focal point is going to be a negative number. So let's look at one example. Okay, this is example 32-7. In this, we are given a radius of curvature that is negative 16 centimeters. That means our focal length is negative 8 centimeters. The object is 10 centimeters in front of the mirror, and the object's height is not given in the example, so we'll make up the height. We'll say that the object has a height of 2 centimeters. If we want to get the location, 1 over f dO plus di, that's going to be 1 over negative 8 equals 1 over 10 plus 1 over di. If I was going to get a common denominator, I would probably pick 40 di. And like I say, really I don't do it this way, I do it with the calculator. This is negative 5 di. This is going to be 4 di. This is going to be 40. We end up getting negative 9 di equal 40, or di equals negative 4 point, I'm sorry, is that right? Yes, 4.44 centimeters. So the image is going to be, I'm sorry, that's the wrong way here. Back here at 4.4, the object was out here at 10. If I want to get a magnification, it's negative di over do. That's negative 4.44 divided by 10. Oop, that's positive. It's a negative of a negative. So 0.444. If the original height of the object was 2 centimeters, 2 times this is going to be so a little less than 1 centimeter tall. All right, that concludes our lesson over the concave and convex spherical mirrors. I'd say the most important thing to remember is that concave mirrors have positive focal lengths and they focus parallel rays, and convex mirrors have negative focal lengths and it causes parallel rays to diverge.